tactics and scouting in this scenario. So now I'm going to present the idioms that we use within our agent to build this multi-scale reasoning within our agent, and ideally create an agent at the level of Flash, programmer here pictured. So the idioms I'm going to present are daemon behaviors, message passing, managers, and micromanagement behaviors. In this talk, I'm discussing these idioms within reactive planning. However, I think they could be useful to other AI techniques, and you could expand behavior trees using some of these idioms or other techniques. So the first idiom I'm going to discuss is daemon behaviors. And what this essentially does is spawn a new thread and constantly pursue a new subgoal. So it enables concurrent goal pursuit within the agent. And what we use this for in our agent is to implement what we refer to as managers, which is a subset of the agent that specializes in a competency. So here's an enable code snippet for spawning an income manager. If the agent selects the initialized agent behavior, what happens is the income manager gets spawned, and then the income manager persistently pursues the goal of mine minerals. And this now is going to occur in parallel with the initialized agent behavior that was first selected. So what's going to happen is the income manager will now be looping, trying to pursue the mine minerals goal, while it will continue and print the status that it started this daemon behavior. Next up is message passing, which we're using to implement communication between different components within our system. So we have two types of behaviors. We have producer behaviors that will actually post state to the agent's working memory, and consumer behaviors that will operate on that and then remove it from memory. And currently our system uses a polling-based approach in consumer behaviors. And we use this to communicate between the different competencies such as tactics and scouting to create this level of control I mentioned. And this is implemented using mental acts enabled to update the agent's working memory. So an example, producer behavior is shown at the top. Essentially, it creates a message and adds it to working memory. In an actual behavior, you would have some set of preconditions that make sure some condition's true, and the message would be parameterized by the preconditions somehow. On the bottom is a consumer behavior, which is polling for message WIMI objects. Whenever one's found, it's bound to the message variable and then deleted from working memory. Then the consumer behavior operates on that message. So we're using the concept of managers, which was first identified in the Abel Wargas paper, and the goal of this is to conceptually partition StarCraft gameplay into specialties. So you don't try to build an agent that knows how to do everything. You try to first split it up into a modular approach where the strategy manager, which is doing high-level strategy, doesn't have to know all the low-level details. An example of this is there's a construction manager in our agent that handles actually selecting worker units for constructing buildings, deciding on a location to build it, and then actually handling the construction feedback. So the strategy manager simply says, I want to construct this building, and then the construction manager executes all the actions associated with that. And essentially, the managers define APIs between the different components, and we use message passing to communicate. So EISBot contains a manager for each of the competencies I mentioned earlier. And here's a visualization of how some of this works. At the high level, there's the strategy manager, which is making the high-level decisions and issuing commands to the lower-level managers, such as the income manager will be told to build worker units and gather resources. It's up to the income manager to decide the rate at which different resource types should be allocated. The construction manager, as I mentioned, actually gets the task of building a specific building, but no specifics of where to build it, what units to use to build it, or what to do if it fails. It's up to the construction manager to handle that. The tactics manager is responsible for attacking the opponent when given a message to do so. And then there's the scouting opponent, which handles scouting around the base to acquire additional information. So the next idiom I'm going to talk about is micromanagement behaviors, which we use to enable the per unit low-level reactive behaviors within our agent. And we do this by spawning micromanagement behaviors for individual units we want to control. So what our agent is actually doing is on the fly dynamically creating behavior trees for managing individual units. And in order to terminate these, we use context conditions to ensure that the unit's still alive. So if a unit gets destroyed, the behavior tree will be terminated and the agent will continue processing. So here's an example snippet for actually spawning a micromanagement behavior tree. In the top level behavior, the agent looks for a vulture that has not yet been assigned to a micromanagement task. So what happens is whenever it finds one of these, it binds the variable to vulture, and then it sub-goals the micro-vulture behavior. The micro-vulture behavior will then consistently check the vulture as a live condition so it can terminate this behavior if it is destroyed in combat, and then it assigns it to be assigned so it doesn't continue getting spawn micro behavior won't run another micro sub-goal on the same vulture since it's now been assigned to this task. And once it's been assigned, it then consistently pursues this micro action, which could be one of many things such as fleeing from the opponent, placing mines, or harassing a unit. So here's a subset of the behavior tree of our agent at one point in time. What happens is the root behavior spawns several of our manager components. Each manager is persistently pursuing one of several goals. In this example, the tactics manager is looking for vultures to assign to micromanagement tasks. The production manager is consistently training vultures, and the strategy manager is determining when to attack the enemy. So if a vulture gets spawned, the micromanagement vulture will assign a vulture task to it, and then it will consistently pursue one of these three micromanagement behaviors. Whenever the agent pursues the goal of actually attacking the enemy, a message will be created by the strategy manager. It will be posted to working memory, and then the squad task behavior will consume that message, and then the vulture will then participate in a group behavior instead of individual behaviors. So we've evaluated our system in StarCraft, and we interfaced with StarCraft using the Brood War API. This enables us to read game state information from StarCraft as well as issue orders to commands. In the paper, we evaluated our work against the built-in StarCraft AI, and currently our system plays only the Terran race. And we evaluated on 3 maps, which are professional gaming maps in widespread use. So this table shows the results of our agent against the built-in AI of StarCraft. We were able to achieve a 66% win rate after 180 matches were played. And against each of the different races, it performed about the same. However, on the map destination, our agent ran into trouble and performed slightly worse than in the other scenarios. And this was mainly due to issues with not enough logic implemented on the construction end of our agent. So we look to improve these numbers as we add specialization behaviors. So now I'm going to actually show a video of the agent in action. At the top are vulture units, which are fleeing from these opponent units and then also placing mines at the same time. And what you'll see is once the agents decide to actually move out of the base now, so several more forces are coming down, and the vultures are then joining in the behavior. And what you'll see next is the agent actually continuing its assault against the opponent, and the vultures are now used to support the tank, which is the unit in the top left, instead of simply just running away. So they're now actually being used to basically be fodder to take damage instead of the tank in this combat situation. More recently, we've actually evaluated our system against human opponents online. We did this by running our agent on the International Cyber Cup, which is what professional players actually train on. It's for non-casual players, people very serious about StarCraft. And we ran 100 matches of our agent against anyone who would join it. We achieved a win rate of 37%, which is pretty good considering that when you look at the ranking, we actually outranked 48% of players on this ladder server. So the way iCup works is you start with a provisional ranking of 1,000 points. If you lose points. If you win, you gain points. And our system was able to achieve 1,182 points rather than losing points, which a typical casual player would do if they tried to play on this server. So in conclusion, I've introduced multi-scale game AI, provided idioms for implementing this within an agent, demonstrated it, and evaluated it. And that concludes my talk.
Just wait for the microphone because we have people following the live streaming.
So what opportunities do you see for learning in this kind of an architecture?
So where learning is going to be implemented is within each of these managers, there's opportunity for applying some learning algorithms. So for example, the tactics manager could make use of Monte Carlo tree search being applied to real-time strategy games. So instead of everything being human authored by Reactive Plan, you could say specialized tactics by having the tactics manager implemented with Monte Carlo search to decide what actions to perform rather than the reactive planning agent. And part of my dissertation work is looking for more and more opportunities to actually apply learning through the use of game replay mining.
More questions? More questions? Amazing.
Or Alex has one.
I had a question about you said the trees for the vultures are sort of dynamic. Is that something you're doing because Abel's a very dynamic language, but couldn't you do it easily with a static tree as well?
So the actual tree for each unit is static, but I mean the spawning a new tree for the vultures is happening within the agent, so there's not an external mechanism doing that.
Okay, gotcha. Thanks.
So it's kind of a uniform architecture for expressing the processing of the agent.
Wondering about the comparisons. So you tried against the intelligence target AI. As Alex said, is in next week. Doesn't that one cheat?
Both are cheating with perfect information at this point.
Okay, so your one has perfect information.
Yes.
How does it handle the perfect information?
I'm working on that. Open research question.
And how does it work against other startup AIs?
That remains to be seen as well.
Okay, so that's supposed to be seen in one of the next few days.
Yes, and then there's also the AID 2010 StarCraft competition, which will have a number of opponents to evaluate against.
I have one last one. Will it make sense to evolve the behavior trees, you think, or parts of it?
So one of the possible future research direction is Michael's explored is integrating reinforcement learning into Able and actually enabling partial programming where you only partially specify the agent's behavior and the rest is learned by training a policy by actually playing games in the domain. So instead of specifying conditions for the agent, you specify a reward function. And that's where you could actually integrate learning within the planner.